In this video, we will discuss binding energy, mass defect, and the strong nuclear force. We will solve practice problems to reinforce our understanding of these concepts. Finally, we will work through an MCAT passage to see how binding energy and the strong nuclear force are tested and presented on the MCAT exam. All material around us is made from matter, and matter is made from molecules. If you break down a molecule, you will get the very basic building block, which are called atoms. Atoms are the smallest unit or building block of all the matter and all that is around us. This is the structure of an atom. An atom is mostly composed of empty space. An atom consists of the nucleus and the surrounding electron clouds. In the nucleus of an atom, which is located at the center of the atom, you have a number of protons and neutrons. Protons are positively charged and neutrons have no charge. The number of protons and neutrons for different elements on the periodic table varies. It's different. So, a number of protons and neutrons are tightly packed inside the nucleus of an atom. Electrons, which are negatively charged, surround the nucleus. Electrons do not have a fixed position. They exist in different energy levels or orbitals. Orbitals are the probability clouds around the nucleus. These electrons are very important in different facets. The properties of electrons, especially the valence electrons, largely determine chemical reactivity, bonding behavior, ion formation, and much, much more. So now that you are more familiar with the structure of an atom, I have a question for you. Since electrons are negatively charged and protons are positively charged, what prevents electrons from collapsing or falling into the nucleus? There are a couple of reasons why electrons do not collapse or fall into the nucleus. Electrons only exist at their appropriate energy levels. Let's go over each reason why electrons do not fall into the nucleus, just briefly. The first reason why electrons do not fall into the nucleus is because electrons follow a circular path around the nucleus. The electromagnetic force, which is the force that happens due to the interaction between electric charges and the magnetic field, has the following formula. F is equal to K, which is a constant, times Q1 times Q2 divided by R squared. Q1 and Q2 are both point charges. F is the electrostatic force, as I stated, K is the constant, and R is the radius between 2 point charges. The electrostatic force between protons and electrons point toward the center of the atom. It points toward the nucleus. The equation that I just stated, so the F equals K times Q1 times Q2 divided by R squared. This equation tells us that the protons and electrons are attracted to one another, and electrons are pulled toward the nucleus. So, if this equation points to the fact that electrons are attracted to protons, what prevents electrons from falling into the nucleus? Electrons move very fast, following a circular path around the nucleus. The velocity vector for each electron is tangent to the circular orbit, and the electrostatic force points toward the center, as we stated. The velocity vector and the electrostatic force are perpendicular to one another. So the velocity of the electron points away and the electrostatic force points toward the nucleus. This action causes the electron to follow a circular path around the nucleus. Think of this like the planets orbiting the sun. The force of gravity pulls each planet toward itself. However, the planets are moving so fast, which prevents them from falling into the sun. And each planet is then forced to follow a circular path orbiting our sun. The second reason why electrons do not crash into the nucleus is because electrons are forced to exist in a quantized energy level. Quantized energy levels follow an integer value, and those integer values are like 1, 2, 3, 4, and so on. There are no fractional values like 2.5 or 3.5. So electrons can only exist at certain energy levels. They cannot Electrons cannot exist in between energy levels, so an electron will not fall between 1.5 or 2.5 energy levels. They can only exist at n equals 1, and n is the energy level. So they can only exist at n equals 1, n equals 2, or n equals 3, and so on. The wave nature of electrons only allows them to occupy certain standing wave patterns around the nucleus. That's why only discrete or quantized energy levels are possible. The lowest, most stable energy state for an electron is at their ground state and not the nucleus. The third reason why electrons do not crash into the nucleus is because of Heisenberg's uncertainty principle. This principle states that one cannot know the position and the momentum of an electron at the same time. So if the momentum of an electron is known, the position of that electron cannot be known for certain. So the exact position and the exact momentum of a particle cannot be simultaneously known. Electrons are always moving and they follow a wave particle duality. Electrons acquire both a wave like quality and sometimes behave like particles. So, these were three reasons why electrons do not fall into the nucleus. Now, I have another question for you. Since protons are positively charged and neutrons have no charge, what keeps them so closely packed inside the nucleus? And what prevents protons from repelling one another at such a short distance? The distance between two protons inside the nucleus is about 1 femtometer, and 1 femtometer is about 1 times 10 to the minus 15 meters. Think about this question. Why don't protons just repel one another? How can they exist so close together at the nucleus? Since protons are positively charged, it is their natural tendency to repel one another. However, protons are closely packed together with neutrons inside the nucleus. The force that overcomes the repulsive force between protons is called the nuclear force, the strong nuclear force. It is the strong nuclear force that holds the protons and neutrons packed tightly together inside the small distance in the nucleus. The nuclear force is the strongest known force in the universe. This force acts at a very short distance and it overcomes the repulsive force between protons. So it is the strong nuclear force that keeps protons and neutrons packed tightly together inside the nucleus and it overcomes the repulsive force between positively charged protons. Let's now introduce the concept of binding energy. Binding energy is the energy that is required to break the nucleus apart. It is the energy that is required to separate protons from neutrons. On the other hand, when protons and neutrons come together to form the nucleus, they release energy, and this energy release is the binding energy. So, binding energy is the energy that is required to break the protons and neutrons apart. It is also the same energy that is released when protons and neutrons come together to form the nucleus. Binding energy can tell us a lot about the stability of the nucleus. The higher the binding energy, the more energy is required to break the nucleus. The higher the binding energy, the more energy is required to separate nucleons. Nucleons are protons and neutrons. The nucleons, which are protons and neutrons, are more tightly bound when there's a higher binding energy. A higher binding energy translates into a higher mass defect. We're going to discuss mass defect in a little bit more detail just shortly. The higher the binding energy also translates into a more stable nucleus. On the other hand, when the binding energy is lower, there is a lower amount of energy required to break the nucleus. There is a lower amount of energy that is required to separate the nucleons, which are protons and neutrons. And these nucleons are they are less tightly bound. There's also the lower the binding energy translates into a smaller mass defect, and when the binding energy is lower, the nucleus is also less stable. So, what is mass defect? The mass of an atomic nucleus is less than the sum of individual masses of protons and neutrons. If you weigh protons and neutrons separately, their total mass will be greater than the sum of the actual mass of the nucleus. This difference in mass is called the mass defect. So the mass defect is actually shown by this formula at the bottom. The mass defect is equal to the mass of the proton plus the mass of the neutron. These are free nucleons minus the mass of the actual nucleus. The mass defect and the binding energy can be explained by Einstein's famous formula. This formula is the E equals mc squared. In this equation, E is the binding energy, m is the mass defect, and c is the speed of light, which equals to 3 times 10 to the 8 meters per second. Binding energy is also directly proportional to mass defect. This is an important point. So when protons and neutrons come together inside the nucleus to form the nucleus, energy is released. This release of energy accounts for the difference in mass. The bound nucleus has less mass than the sum of its free components. Let's go over some practice problem to test our understanding of the concepts that we just learned. Here's the first question. Calculate the mass defect of a helium-4 nucleus. Mass of proton, neutron, and the actual mass of the nucleus are given. So take a minute, pause this video, work through this problem by yourself, and then come back and see how we answered this question. So in order to answer this question, we first need to figure out the number of protons and neutrons inside the helium-4 nucleus. There are 2 protons and 2 neutrons inside the helium-4 nucleus, and the formula for mass defect is the sum of the masses of individual or free protons and neutrons minus the actual measured mass of the nucleus. So we need to multiply the mass of protons, which we have 2, by the number or the mass that we are given. So we need to multiply 2 times 1.6726 times 10 to the minus 24 grams. That equals a value of 3.3452 times 10 to the minus 24 grams. This value equals the total mass of protons, free protons. Then we need to multiply the mass of neutrons by 2 because there are 2 neutrons inside the helium-4 nucleus. So we have to multiply 2 times 1.6749 times 10 to the minus 24 grams. And we get a value of 3.3498 times 10 to the minus 24. This is the total mass of free neutrons. Since helium-4 nucleus is composed of 2 neutrons and 2 protons, we need to add the total masses of free protons and neutrons that we just obtained. After we do that, after we sum the two masses of free protons and neutrons, we get a value of 6.695 times 10 to the minus 24 grams. This is the total mass of free protons and neutrons. The equation for mass defect requires that we subtract the actual measured mass of the nucleus from the sum of the free protons and neutrons. When we do that, when we subtract the two numbers from one another, we get a final answer of 0.049 times 10 to the minus 24 grams. This is the mass defect. And as you can see, the actual measured mass of a helium-4 nucleus is not the same as the sum of free protons and neutrons. Once protons and neutrons come together to form the nucleus, some energy is lost. And this energy loss translates into a loss of mass according to E equals mc squared formula, or the Einstein's formula. Binding energy and mass are directly proportional to one another. So a loss of energy due to the binding of free protons and neutrons translates into a loss of mass. Let's work on another problem to see how we can calculate the mass defect and also this time the binding energy as well. So number 2 reads, calculate the mass defect of lithium-7 in kilograms. What is the binding energy per nucleon in lithium-7 in joules? The mass of protons and neutrons are given. The measured mass of the lithium-7 nucleus is also given. Take a minute, pause this video, work through this problem by yourself, then come back and see the solution to this problem. So here's the solution to this problem. And in order for us to figure out the answer to this problem, we need to find the number of protons and neutrons in the lithium-7 nucleus. The number of protons inside the lithium-7 nucleus is 3. So we have 3 protons and 4 neutrons. We then need to figure out the sum of the masses of free protons and neutrons. In order to do that, we need to figure out the combined masses of the 3 protons and the 4 neutrons. So once we multiply 3 by 1.6726 times 10 to the minus 24 kilogram, we get a value of 5.01786 times 10 to the minus 27. This is the total mass of free protons. Then we need to multiply 4 because we have 4 neutrons inside the lithium-4 nucleus. We need to multiply 4 by 1.67493 times 10 to the minus 27 kilogram. Once we do that, we get a value of 6.69972 times 10 to the minus 24 kilogram. This is the total mass of free neutrons. Once we add the total mass of free neutrons to the total mass of free protons, we get a value of 1.1758 times 10 to the minus 26 kilogram. Then we need to plug this number into the mass defect equation. So we need to subtract the actual mass of the nucleus from the mass of the sum of the free protons and neutrons. Once we subtract these two values from one another, we get a value of 0.00 0.7758 times 10 to the minus 26 kilogram. This value is the mass defect, or the difference between the sum of masses of free protons and neutrons minus the actual measured mass of the nucleus. The second part of this question asks for the binding energy of lithium 7 nucleus. So to answer this question, we need to use the E equals mc squared formula. E is the binding energy in joules, m is the mass defect, and c is the speed of light. So E is equal to 0.007758 times 10 to the minus 26 kilogram times 3 times 10 to the 8 meters per second. And you have to square that value because the equation requires that you square the c value, or the speed of light. If we plug this into our calculator, we get a value of 6.98 times 10 to the minus 12 joules for binding energy. If you are asked to calculate the binding energy per nucleon, you simply need to divide the binding energy above by the number of nucleons, which in this case, for the lithium 7 nucleus, there are 7 nucleons. Nucleons are the number of protons and neutrons. Once we divide our binding energy by 7, we get a value of 9.97 times 10 to the minus 13 joules per nucleon. And this answers number 2. Number 2, it asks the binding energy per nucleon for each of the following nuclei is given. Which of the following atomic nuclei is the most stable? The binding energies are given in MeV. This stands for mega electron volts. Mega electron volts are just another unit of energy. Just like how joules is a unit of energy, mega electron volts is also another unit of energy. So this question is asking for the most stable nucleus. Which one do you think is the most stable nucleus? Take a minute and think about this question. So here's the answer to this question. We said before that a higher binding energy means that more energy is released when protons and neutrons come together. And if more energy is released when protons and protons and neutrons bind, this means that the nucleons are held more tightly in the nucleus, which makes the nucleus more stable. So we need to look for an answer choice with a higher binding energy per nucleon. K39 has a binding energy of 8.55 megaelectron volts per nucleon. So K39 is the most stable out of all the other options. So answer choice B is the correct answer. Question number 3. The binding energies per nucleon of some of the elements are listed below. Which of the following has a smaller mass defect? These values are given in mega electron volts per nucleon, so the binding energy of each nucleon is given, but the question asks for the smaller mass defect. Which one do you think has the smallest mass defect? Here's the answer to this question. Binding energy and mass defect are related to one another by the formula E equals mc squared. Binding energy and mass defect are directly proportional to one another. This question is looking for the atomic nuclei with the smallest mass defect. An element with a smaller mass defect would need to have a smaller binding energy per nucleon. So the smallest binding energy per nucleon out of all the options that are listed is BE9. So that is answer choice A. So answer choice A is the correct answer. Number 4. The mass defect values for the atomic nuclei of the following elements are listed below. What fundamental force is responsible for the mass defect observed in these nuclei? So now you are given mass defect values and you're asked about which force is responsible for the mass defect. Which one do you think is responsible for the mass defect? So the solution to this problem is C. Here's the reason why. Recall that mass defect is equal to the mass of free nucleons minus the mass of the actual nucleus. This missing mass corresponds to the binding energy that holds the nucleons, which are protons and neutrons, together. The force that is responsible for holding protons and neutrons bound in the nucleus is the strong nuclear force. Option answer choice A and B, they represent the same force. The electrostatic force is the Coulombic force, and this force causes protons to repel one another. It does not hold the nucleus together. The weak nuclear force, which is option answer choice D, is responsible for radioactive decay. It is not responsible for binding. So the correct answer to this question is C, which is the strong nuclear force. Question number 5. The mass defect values for the atomic nuclei of the following elements are listed below. Which of the following has the greatest difference in mass between its corresponding free nucleons and the actual nuclear mass? So we are given mass defect values and asked to find the greatest difference in mass between the corresponding free nucleons and the actual nuclear mass. Which one do you think is the correct answer? Take a minute, pause this video, think about it, and then come back and see the solution. So this question is basically asking you which of the following atomic nuclei has the greatest mass defect. The mass defect values are given, and we are only asked to pick the option with the highest mass defect value. So option number C, answer choice C, is the correct answer because it has the highest mass defect value. Number 6. Which of the following best describes the role of the strong nuclear force? A. It prevents electrons from falling into the nucleus. B. It binds protons inside the nucleus. C. It counteracts the electrostatic repulsion between protons. D says both B and C. E is all of the above. Which one do you think is the correct answer choice? So let's go through each answer choice and see which one is correct and which one is not correct. Answer choice A, it says it prevents electrons from falling into the nucleus. The circular path of electrons, the quantized energy levels, and the Heisenberg uncertainty principles, they are responsible to explain how electrons do not collapse into the nucleus. So answer choice A is not correct. It's false. Option B. It says it binds protons inside the nucleus. Option B is correct because the strong nuclear force explains how both protons and neutrons bind to form the nucleus. Option C. It says the strong nuclear force counteracts the electrostatic repulsion between protons. This answer choice is also correct because without the strong nuclear force, protons would repel one another and they would fly out of the nucleus. So both options B and C are correct, which makes Answer choice D, the correct answer. And here's the solution, a full explanation to question number 6. So answer choice D is the correct answer. And answer choice E is wrong because option answer choice A is also wrong. So now that you have a better understanding of the strong nuclear force, binding energy, and the mass defect, let's work through a sample MCAT style passage. But before we start, let's review some tips on how to tackle MCAT science passages. First, read the entire passage and focus on the main idea. Do not get tangled in minute details. Acknowledge important details by highlighting them or jotting very brief notes on the scratch paper that you're going to be provided on test day. Read each question very carefully. If a question is not clear, rewrite it in your own words so you know exactly what the question is asking you. Read every answer choice before choosing and return to the passage when the question requires it. Combine the passage information with your background science knowledge to arrive at the best answer. Remember that most MCAT answers are not stated verbatim in the passage, so you will often need to infer using both passage evidence and your prior knowledge. Finally, manage your time. Flag difficult items and come back to them, and never leave a question blank. This passage will only test your understanding of what we just learned in this video. I recommend that you pause this video and work through this passage on your own. Then resume this video to see the full explanation to the questions and a full passage analysis. So here's the passage. Let's begin. In the past, scientists believed that the mass of an atom was equal to the sum of the individual masses of its protons and neutrons. However, in 1919, the British physicist Francis Aston challenged this long held view with his mass spectrograph experiments. He observed that the measured mass of an atomic nucleus is slightly less than the sum of the masses of its individual protons and neutrons. This difference is now understood as the mass defect, which reflects the binding energy of the nucleus. To describe this discrepancy, Aston introduced the concept of packing fraction. It's defined as F equals ma minus a over divided by a, where ma is the actual atomic mass in atomic mass units and a is the mass number, the total number of protons and neutrons. The packing fraction is therefore a relative measure of the mass defect per nucleon. Aston's discoveries, combined with Einstein's famous formula E equals mc squared, laid the groundwork for understanding nuclear binding energy and the stability of atomic nuclei. Nuclei with a more negative packing fraction are more tightly bound. The following graph represents Aston's results. Here's figure 1. Packing fraction versus mass number for some elements. Question number 1. Why is there such a large difference in packing fraction between hydrogen and helium nuclei? Question number 2. Based on figure 1, Which of the following atomic nuclei has the highest binding energy per nucleon? Question number 3. Why does the packing fractions show such a sharp increase from helium to lithium as presented in figure 1? Question number 4. If a newly discovered isotope has a packing fraction close to zero, what can be inferred about its nuclear stability? So, after you have read the passage and worked through the problems on your own, come back and we're going to go over the passage analysis together and solve all the problems together. So, here's an analysis of the passage. Let's go through each paragraph and point out important information. After you read this passage, you should realize that this passage is about mass decay, binding energy, and packing fraction. So, paragraph number 1, it says in the past, scientists believed that the mass of an atom was equal to the sum of the individual masses of its protons and neutrons. However, in 1919, the British scientist Francis Aston challenged this long held view with his mass spectrograph experiment. He observed that the measured mass of an atomic nucleus is slightly less than the sum of the masses of its individual protons and neutrons. This difference is now understood as the mass defect, which reflects the binding energy of the nucleus. So, this first paragraph introduces the concept of mass defect. It provides historical context about earlier beliefs. It discusses Aston's discovery, explains what mass defect is, and it connects mass defect to its binding energy. Paragraph number 2 describes this discrepancy. Aston introduced the concept of packing fraction. The formula is given, and the various different variables are explained. It says the packing fraction is therefore a relative measure of the mass defect per nucleon. So paragraph 2 introduces packing fraction formula to better explain mass defect. Paragraph number 3. Aston's discoveries, combined with Einstein's famous formula, laid the groundwork for understanding nuclear binding energy and the stability of atomic nuclei. This sentence is important, this following sentence. Nuclei with a more negative packing fraction are more tightly bound. And then it introduces the graph. So in paragraph 3, Einstein's famous formula is introduced, and it is connected to the packing fraction formula to explain mass defect, nucleon binding strength, and nuclear stability. The figure is also shown, which is a graph of packing fraction versus mass number for some elements. The main idea of this passage is that this passage is mostly about packing fraction, mass defect, and binding energy. So the answer to question number 1 is B, but let's see why. The question number 1 states, why is there such a large difference in packing fraction between hydrogen and helium nuclei? So for this question, we need to refer to figure number 1, the only figure in this passage. So as you can see from the figure, the packing fraction for hydrogen is close to 0, and the packing fraction for helium is between -6 and -8. So the answer to this question is B. As stated in the passage, packing fraction relates to how tightly nucleons are bound. Hydrogen nucleus, which only has one proton in its nucleus, has almost no binding energy. So the only proton has no neutron to bind to, which makes its packing fraction close to zero. And it makes hydrogen less stable than helium. Therefore, options or answer choices A, C, and D are all false. D is wrong because one cannot determine nuclear stability based on atomic size alone. The helium 4 nucleus has a very high binding energy per nucleon. It has a large negative packing fraction, very tightly bound nucleons, and high binding energy, and a high mass defect. This makes option B the correct choice. Question number 2. Based on figure 1, which of the following atomic nuclei has the highest binding energy per nucleon? So to answer this question, we also need to refer back to figure 1. It's asking which one has the highest binding energy. So as it was stated in the passage, packing fraction relates to how tightly nucleons are bound. A more negative packing fraction results in a more tightly bound nucleus. This translates into a larger binding energy per nucleon. The element with the most negative packing fraction is iron, Fe. So option D is the correct choice. All the other options show higher packing fractions than iron. Question number 3. It says, why does the packing fractions show such a sharp increase from helium to lithium as presented in figure 1? Answer choice A states the nucleons of lithium experience a larger binding energy. B, the mass defect of the lithium nucleus is larger. C, helium nucleus presents a smaller binding energy release per nucleon. And D, lithium nuclei contain additional nucleons that are less tightly bound. Answer choice D is the correct answer. And helium 4 has 2 protons and 2 neutrons. This makes it extra stable and it gives it unusually high binding energy per nucleon. Lithium adds an extra proton and neutron, but these nucleons are not as tightly bound. A is wrong because binding energy per nucleon actually drops going from helium to lithium. Answer choice B is also not correct because helium has a relatively large mass defect per nucleon. Answer choice C is not correct because helium has a greater binding energy per nucleon. Answer choice D is the correct answer because lithium contains additional nucleons that are less tightly bound, which explains the sharp increase in packing fraction. Question number 4. If a newly discovered isotope has a packing fraction close to zero, what can be inferred about its nuclear stability? So you have to use information from your background knowledge as well as the information that's presented in the passage to answer this question. For stable nuclei, the packing fraction is negative, which means lots of binding energy is released. If the packing fraction is close to zero, that means the nucleons are not tightly bound, which leads to a smaller binding energy release per nucleon, and this corresponds to the nucleus not being very stable. Option A is not correct because a large amount of binding energy release corresponds to a larger negative packing fraction, not a near zero packing fraction. Answer choice B is false because a near zero packing fraction means mass defect is also very small. Answer choice C is the correct answer because a near zero packing fraction means weak binding of the nucleons and lower stability. Answer choice D is not right because it contradicts near zero packing fraction. So in this video, we went over mass defect, binding energy, the strong nuclear force. We also practiced some problems and we also solved an MCAT style passage. And so, if you found this video helpful, please like and subscribe for more content and helpful tips. Thanks for watching and happy studying.